and we all look forward to your seminar, Dr. Yano.
Thank you so much, Jerry, and thank you everyone for being here. So let's see. I'm not that early career, unfortunately. I should have asked the early career people to speak about this, but we'll see. So I'll be talking about what we do at X-ray free electron lasers, and our group is interested in metalloenzymes. So there are many different kind of metalloenzymes. I think about 30% of enzymes are metalloenzymes, and there are many energy-related ones, and also in our body, health-related metalloenzymes. So these enzymes are doing quite complicated chemistry using the flexibility, like a multi-oxidation state chemistry at the metal site, and the flexibility, using the flexibility of protein environment for electron transfer, proton transfer, and the substrate product transport, and many more functionality. So we would like to know how this complicated chemistry in metalloenzyme is possible by learning using spectroscopy and X-ray crystallography. Since this is a spectroscopy-oriented audience, I will focus more on the spectroscopy side. So, as I said, our goal is to understand how the protein environment controls multi-electron, multi-proton reaction. So these are very difficult reaction to do if we want to use inorganic materials and do catalytic reactions. So that's what we would like to learn, almost like a natural systems as our textbook. So to do that, we want to know the structure of enzymes, as well as metal chemical state of metal catalytic centers. For that, we want to do crystallography, or in this case, cryo-electron microscopy can be used quite intensively. Or we can, for the metal chemical state of metals, we can use X-ray spectroscopies. So that's what I will be talking about. I'll focus on two topics. One is how we are combining X-ray emission spectroscopy with the structural studies, more specifically crystallography, and try to do it under physiological temperature using X-ray free electron laser facilities here. Then the second topic is we want to enable X-ray spectroscopy method for metalloenzymes at XFELs. Of course, X-ray spectroscopy is widely used at the synchrotron facilities, but there are some difficulties at the free electron lasers for certain methods. So we are trying to enable some of these methods for specifically for metalloenzymes. So that's my topic today. As I said, in order to understand metalloenzyme functionality, we want to do crystallography and X-ray spectroscopy. So crystallography tells us the structure and the structural dynamics if we do a study at room temperature by triggering reaction and following it. And X-ray spectroscopy, because of the element selectivity of the spectroscopy, we can look at chemical changes at the catalytic site. So if we focus on X-ray spectroscopy of metalloenzymes, the challenges are that, first of all, it's often quite dilute. So the metal concentration is often less than 1 millimolar, then how to get such kind of signal uniquely is one challenge. And the second is that sample is quite often quite limited. Therefore, we cannot use a liquid jet with the high flow rate. So how to work around it? And the third challenge is that this is more for the soft X-ray region of the spectroscopy. How to work with the light atom backgrounds. For example, in case of manganese, oxygen KH, manganese LH, oxygen KH is very close. So how to get the manganese signal with such high background situation. So those are the challenges. And in this talk, I will use Photosystem II, which does a water oxidation reaction, this reaction, as an example, and how we are working on X-ray spectroscopy on these systems. So that's what I will be talking about. Okay, Photosystem II, this is the chemical cycle, catalytic cycle of Photosystem II for water oxidation reaction. So in Photosystem II, two waters are split into one molecular oxygen, 4 protons, and 4 electrons with the absorbed light. So chlorophyll center here, reaction center here absorbs red light, and then charge separation happens. Electron goes to the acceptor side, and the hole or positive charge goes to the donor side, where oxygen evolving complex is. So this oxygen evolving complex consists of 4 manganese. Here in this case, these are the purple colors. These are oxo-bridged, which are red, and there is 1 calcium in it. In the ligand environment, so the cluster has 4 terminal waters, 2 at calcium, 2 at manganese, and then there are 6 carboxyl and 1 histidine ligands around here. So when we put this sample in a dark, it settles down to the state called S1 state, in which the oxidation state of manganese is 3,344. And then after first photoexcitation and charge separation, S1 state goes to the S2 state. One of the manganese is oxidized, so it becomes 3,444. With the second excitation, S2 state goes to the S3 state. All 4 manganese becomes formally 4 plus oxidation state. And then with the third illumination, S3 state goes all the way from S3 to S0 state. And S0 state oxidation state is 3 manganese 3 plus and 1 manganese 4 plus. So this is the catalytic cycle. Our goal is to understand how the catalytic structure, the manganese oxygen evolving complex, the structure changes during the catalytic cycle. And we want to follow this under ambient physiological temperature as the reaction occurs. So this is Photosystem II water oxidation reaction. It's I would say it's an interesting, good system to go through time-resolved work, because the phenomenon is spread quite broadly, starting from the charge separation, which occurs around the picosecond timescale. So we can follow by photoexcitation, we can look at the various phenomena from the charge separation, charge stabilization, down to the catalytic reaction, which is more later phenomenon, like a microsecond, millisecond timescale. So this catalytic reaction occurs much later, not because that atoms or electron moves so slowly for catalytic reaction, but because of the event which needs to happen beforehand. So ideally, we would like to look at various time points to see how things occurs in a time and space. This photosystem II has been studied quite a long time at the synchrotron facilities, more recently at the XFEL. At the synchrotron, large part of the work was done to capture the structure or electronic structure of the manganese cluster for stable intermediate states like S1, S2, S3, and S0 state under cryogenic temperature using various X-ray spectroscopy method like X-ray absorption spectroscopy, Zane's EXAFS, or RIX type spectroscopy. All these data are available. And there are some effort to do experiment at room temperature as well. So it is possible to do room temperature data collection even at the synchrotron facilities. What I'll be talking about here is what we are doing at the free electron laser, X-ray free electron lasers. So here, our target is to do experiment under room temperature using crystallography and X-ray spectroscopy to follow a sequence of event and look at the structure and the chemical dynamics. So sometimes we use single crystals of photosystem II to do structural studies with crystallography, but simultaneously we can also do X-ray emission spectroscopy to look at the oxidation state of the metal catalytic centers. And then we can also do X-ray absorption spectroscopy. So I'll be talking about these spectroscopies. From the spectroscopy side, at the XFEL, we started with the X-ray emission spectroscopy because it is easier to do X-ray emission spectroscopy than absorption spectroscopy at the XFEL. The reason is that we can use this XFEL SASI beam, spontaneous amplified beam like this, which has a certain bandwidth. It's about 20 to 40 electron volt. Fluids have maximum. So we don't need to monochromatize it, and we can use this beam shot by shot. And we need to replace sample shot by shot. So we are flowing samples, solution, or single crystal samples like this way. And then we collect emission spectrum using von Hermann's spectrometer. So we use energy dispersive spectrometer. And then if it's a transition metal, we can collect K alpha or K beta spectrum. And one of the biggest advantage of XCS is that we can combine with the diffraction or scattering method, because incoming X-ray energy can be the same for crystallography and X-ray emission spectroscopy. So we are using around 9.5 kilo electron volt X-rays, which is about 0.9 angstrom. Therefore, we can use for excitation of the emission spectroscopy, as well as for crystallography. If you were to do X-ray absorption spectroscopy, it's a little bit more involved because we need to monochromatize incoming X-rays. That means that we lose quite a large portion of the photons. And we need to scan incident X-rays through the energy range of Zen's 50 eV, or if it's exa's, several hundred electron volt. Another challenge is that we need to deal with many kind of fluctuation. So incoming X-ray intensity fluctuates a lot, and probably the probing volume of sample fluctuates quite a bit. So how to normalize data, absorption data through the Zen's or exa's energy range accurately. So that's a kind of challenges. So I'll be talking about starting from X-ray emission spectroscopy. And in both cases, we want to use as small volume of sample as possible for the experiment. So for that purpose, we instead of liquid jet, we decided to use this drop-on tape system. It's a combination of acoustic transducer, which creates a droplet of samples. It can be a solution of metalloenzymes or a single crystal suspension. And then we put this onto the conveyor belt that takes the sample to the X-ray intersection point right here. And then X-ray comes and we can do diffraction at the downstream and the X-ray emission spectroscopy at the orthogonal directions. The reason we decide to use this geometry is that between the droplet formation and the X-ray intersection point here, we have a kind of reaction region where we can do photoexcitation experiment or substrate mixing experiment. So actual system looks like this, and so this is the continuous tape. This is the acoustic transducer, which produce droplet using the power of sound wave. The droplet size is about 200 micrometer diameter. And so for photoexcitation, we have a fiber-coupled laser on the way. And then X-ray intersection point is somewhere here. So you can see in this video that droplet is destroyed. So in this case, droplet is coming here, and then it's hit by X-ray, so droplet disappears. X-ray comes with a kind of grazing incident to the tape surfaces. So this is the setup we are using. I'll be talking about is photoactivation using the lasers, but same setup can be used for substrate mixing. For example, we can add the substrate solution on top of solution samples, which is this case. And we can also do gas excitation. For example, we start with the ambient atmosphere and then introduce oxygen gas to initiate some chemical reactions. I think this is the first break for me, probably, if you have any questions.
Well, we'll give people a minute or so to put in questions. My first question is, you talked about the K beta, for example. What about the valence to core region? If you could measure it, do you know if there would be scientific merits?
I think so, yeah. Only that von Harmas geometry, the spectrometer may not be the way to go. So therefore, it's not the first choice of the experiment. Probably using Roland circle is better for reducing the background for the balanced core spectroscopy.
Yeah, it could be. I've wondered about a graphite crystal to select the band and then transition it sensor array. But yeah, it would be quite a challenge, but I think it would be fascinating. Roughly how much time is needed for the reaction region between when the droplet falls on the tape and when it gets brought over and put into the beam?
That can be controlled depending on the position of the acoustic transducer to the X-ray intersection point, and also the tape speed. So combination of those, we can very much control it. In the extreme case, we can create a droplet very close to the X-ray intersection point.
So 100 milliseconds to a few seconds, or what kind of time window?
Right. So I will show you later. So
okay.
The fiber coupled laser is for slower reaction, meaning that a larger time delay for a millisecond. But for the faster time delay, we have a free space laser, one more laser, which is almost coincide with the X-ray intersection point. That can be used for much faster reaction, like 100 femtosecond, picosecond time scale.
Okay. Bianca, you have a question?
Yes. Hi, thanks. It's a great talk and a fascinating method. I was wondering, you said that you have the problems of small sample amounts. So did you check like which metal concentration is the lowest that you can measure with this technique?
Right. Currently, we haven't gone to the extreme concentration, but currently what we can collect comfortably for spectroscopy is 0.4 millimolar, 0.3 millimolar, somewhere there. Of course, if you spend more time, we can collect the data.
How long did this take, 0.3 millimolar?
So, yeah, so depending on whether we can collect within reasonable time, that's the challenge here.
Thanks.
Okay.
Thank you for your question.
Thank you. Ben, you had a question?
Yeah, thanks for the talk, Junko. I was wondering how you quantify various products you form on the tape after the interaction with light or a substrate. Yeah, that's it.
Oh, yes, yes. Yeah, it will be nice to add some diagnostic way to look at how the reaction happens. Depends on the target enzymes. For example, if it's photoexcitation of this Photosystem II, we can look at the emissions data and look at the oxidation state changes to see how look at the advancement of the S state. That's one way that it's using X-ray. Regarding the substrate mixing, we can do similar things, but we are also adding optical spectroscopy capabilities that gives us some signal whether a reaction is happening what we are expecting or not. Regarding the product, for example, mass spec related product formation, that's a bit challenging to detect. So again, we don't need to do everything on site, but what we can do is we have a setup in the lab, copy of the setup in the lab, and then we can create a similar situation, like a mixing speed, a mixing volume, and then do the analysis beforehand, before going into the beamer. Does that make sense,
Okay.
Ben?
Yeah, thank you. Yeah, I was just wondering because I know like in Photosystem, quantifying the individual S-state fractions before, for example, you freeze a sample and measure it is a common step. And I was just wondering how that's achieved in this sort of in situ formation. So, but I understand also that the spectroscopy itself is a probe of this process. So, yeah.
Yeah, that's right. And for Photosystem II case, we do membrane inlet mass spectroscopy and EPR. That is not exactly the same condition we are using for the experiment, but at least we can use exact same sample for that experiment.
Okay, thank you. Junko, you should continue, please.
Okay. So, oh, I forgot about that. So using this setup, what we are doing is photo excitation or mixing. But of course, there are many other groups who are working on a different way of triggering reactions, like temperature jump, Mike Thompson's group is doing. That's one example. And also caged compound for releasing some chemicals with using light. This is Takehiko Tosha's group's studies. So there are many way of initiating reactions. Now I'll be talking about the water oxidation reaction in Photosystem II result. So what we did first was to capture stable intermediate like S1, S2, S3, and S0 state under room temperature. For that, we use these three lasers, visible lasers, fiber-coupled ones. For example, if we want to capture S2 state, we use one of the lasers, S3 state, 2 lasers, and S0 state, 3 lasers, like that. And these are the electron density maps of the manganese cluster. So S1 and S2 state, this is almost close to 100% that pure S state, but going to later state like S3 or S0 is the mixture of state. So for example, S3 state, after second flush, what we get is the 70%, around 70% S3 and 30% S2. If it's after third flush, 60% S0 and 40% S3 state, something like that. So from here, we need to deconvolute data and then create a pure S-state structure. So that's what we did. And then these are the models. What we see is that the structure of the manganese cluster, the basic geometry doesn't change, although the oxidation state of manganese changes. Therefore, the metal-metal or metal-ligand distances are changing. Only exception is the S3 state, where we see the addition of one ligand, additional ligand coming into the open coordination site of this manganese. So between manganese 1 and calcium, we see additional ligand. And next step was not only the stable S state, we wanted to see how one state goes to the next state in what kind of time constant or what kind of kinetics. For example, S2 to S3 state, when this additional oxygen ligand, we think it's OH, when does this one count? To do that, we are using now free space laser counts. So what we can do is we use one of the fiber coupled laser to drive S1 state to S2 state, and then use the free space laser to go to various time points between S2 to S3 state. So that's what we did. And X-ray emission spectroscopy gives us an idea of the manganese redox kinetics. So that's important because that gives us an idea that which time point we should be going to collect the crystallography data. So we used the manganese K beta 1,3 peak first moment, and for example, S2 to S3 state, this is a manganese oxidation happened, so the peak shifts like this way. And from here, we can say that time constant is about 350 microseconds. Using this, we selected the time points of the crystallography and then collected the data, like 50, 150, 250, and 400 microseconds after the second flash. From here, what we can say is that so we start seeing the increase of this OX density starting from around 150 microsecond. And that tells us that probably this oxidation change of manganese 1 from 3+ to 4+ triggers the insertion of the ligand, this OH, into the open coordination site. So by doing crystallography and X-ray emission spectroscopy, we can get this kind of information. After looking at S2 to S3, now we want to go to S3 to S0 state. This is a bit complicated step, interesting step, but it's more complicated. One reason is that S state is more mixed, and also many things are happening. 2 protons need to go out from the cluster, and final oxidation need to happen, which is related to this hypothetical S4 state. And then O bond formation, 2 oxygen comes together to make a O bond, molecular oxygen is released, and substrate water, another water needs to come back in order to reset the catalytic cluster. So many things are happening. To study this step, what we did was using this 2 fiber coupled laser to drive S1 state up to S3 state, and then use free space laser to go to, again, various time points. So that's what we did, and this is what we published actually this year. What we see is in this case, you see this red density, which is this oxygen X, it's disappeared somewhere around this time point. I forgot to write the time point, but I think it's around 600 to 900 microseconds after the third flash. So again, we can get this kind of information. So I'm focusing on the spectroscopy side. I will not go into the details of the crystallography data. So interesting part may be that although we are focusing on what's going on at the metal cluster, metal catalytic site, we can also look at what's happening at the other region of the protein and what is the sequence of event happening at the metal catalytic center and the surroundings, because surroundings surrounding protein, and the hydrogen bonding network plays very important role. For example, for a substrate water has to come into the metal cluster at right time, or proton needs to be released from some of the channels. So how this happens. So these are kind of information we could get from the crystallography side. Again, I'm not gonna go into the details. So what's next? We haven't really seen exact structure or chemical state when O-bond formation occurs or subsequent steps. So, of course, one effort is to do improve the crystallography resolution much more. Currently, it's getting close to 2.0 angstrom, but we need to go beyond that. At the same time, we can do a different type of spectroscopy, which is absorption spectroscopy, and doing XFELs and XFELs that gives us a more detailed electronic structure, as well as local geometry or atomic distance changes of the metal cluster. So that comes my second part, but should I set a break here again?
We'll give people just a minute if anyone has a question. Okay, why don't you keep going, and I'm sure we'll have questions for you at the end.
Sure. So I'll be talking about absorption spectroscopy from here. I already talked about what are the challenges of doing X-ray absorption spectroscopy at the free electron laser. And the source of fluctuation is the issue, probably largest issue. So incoming X-ray fluctuate like this, and then you are setting a small monochromator window. So the intensity, incoming X-ray intensity fluctuate almost from 0 to 100%. And then if you were to use particularly liquid jet, if it's not a stable high flow jet, probing volume will be fluctuating quite a lot. So how to deal with these kind of multiple fluctuation? We decided to use watering by putting a scattering detector at the downstream. So this watering intensity includes the incoming X-ray fluctuation as well as the probing volume fluctuation. So by using this, we can normalize the data through the XFELs region quite well. So that's what we're doing. For Photosystem II, what we want to look at. So what we want to focus is the last step where S3 state goes back to the S0 state after molecular oxygen evolution and reset of the catalytic center. So in a synchrotron at cryogenic temperature, we see this kind of XFELs changes or XFELs changes. Basically, what we want to look at is in between here to here or here to here. What are the questions? Questions may be, what is the electronic structure around the formation of this hypothetical S4 state? It can be transient state, so it won't be visible. That can be one result we will see. And also after that, what is the recovery process? Whether there are some reduced intermediate states, which is like one case scenario is that 2 oxygen comes together and then 2 electron reduction happens. and those two oxygens are hanging around for a certain period of time. And then after that, molecular oxygen is released. So in this case, on the right side, it's a 2x2 electron reduction case. Or instead, things happens almost simultaneously, like as soon as O-bond formation happens, molecular oxygen is immediately released. That may be close to 4 electron reduction in one shot. So those are kind of questions we would like to ask. And again, we are using the exact same setup for the X-ray absorption spectroscopy as well. So this is the data we got from the traditional way of doing absorption spectroscopy using this setup. So we put the detector up here, and using the water ring intensity, we collected data. From 0.4 millimolar manganese, the data collection with the 120 hertz X-ray pulse, it took about 1 hour to get this data, which is not too bad, I would say. There is a hope to get cleaner data by collecting longer time. But we did one more method. One is that is using HERT XAS, high energy resolved fluorescence detected X-ray absorption spectroscopy using analyzer crystals. In this case, we used the K-alpha crystal to by using black reflection to select the K-alpha signal from manganese. By that way, we can reduce the background quite a bit. Probably fluorescence signal is also reduced, but the reduction of background is significant. By that way, we could collect the HERT XAS like this way, and as you can see, quality is much, much better, and the data collection time is much faster as well. So that's what we will be going, or we are trying to do, and this is the actual setup. You can see analyzer crystal here, the detector down here. So that was the KH, manganese KH side of the experiment. And we also want to do manganese LH absorption spectroscopy. For that, of course, we need to go to soft X-ray energy. That means we need to do experiment under vacuum condition. We cannot use tape drive, so we are using a liquid injector for that. So for LH, the challenge is that manganese fluorescence is around 640 electron volt, but oxygen K alpha is 525 electron volt. So oxygen concentration in an enzyme is about 50 molar, but manganese concentration is less than 1 millimolar. So how to live with this kind of huge background is a challenge. And we are working with Philippe Bonnet's group in Uppsala. We are using this setup using zone plate to spatially separate out manganese and the oxygen signal on the 2D detector. So this was a little bit of old data, but mainly for the demonstration purpose. We could collect 0.4 millimolar manganese L3 XAS data. At least it looks like a peak. No, it's above the noise, so we can see something. Still, the issue we have is that in this setup, manganese L alpha signal is sitting at the shoulder of oxygen K alpha. So separation of manganese and oxygen signal is not quite enough in the current setup. So in the new zone plate, we have a better separation of manganese and oxygen signals. So we think that using this setup, we should be able see get a better data of manganese LH. So that's a ongoing study. So to be summarized, we are doing crystallography and X-ray emission spectroscopy at room temperature to connect the structural dynamics and chemical changes or chemical dynamics. And with the XAS at both KH and LH, we want to look at more detailed electronic structural changes as well. So this is my last slide, and I want to acknowledge all my colleagues and many collaborators. So this is a highly collaborative work, and I also want to acknowledge all the facilities at synchrotrons, as well as the free electron lasers. Yeah. Thank you so much for listening.
That was a wonderful talk. Thank you. Thank you so much. People should start typing in their questions to start. George, you had a question?
Yeah, I did. I didn't know when you were comparing the manganese spectra and showed the reduction in signal to background using the Herfty. What kind of I think the first measurement was transmission, if I understood correctly, and so I wonder if you've tried any other, and if that's not correct, what type of detector was that? And if that is correct, then have you tried any other detectors besides the Herfty to see how they might compare?
Oh, actually, detector was the same. I think both cases we used the EPIX 100. That is a 2D detector. So, but the difference, and it's not a transmission actually. We are collecting both fluorescence signals. But in one case, we are adding analyzer crystal to select manganese K alpha with more specifically. And the other one, it's a direct collection of fluorescence.
So the problem is the stray scatter, the stray elastic scatter, yes?
Right, yeah.
Okay. Any thoughts about maybe one of the large curved carbon analyzers that are still often used at synchrotrons to reject elastic scatter?
I mean, like a Roland type crystals?
No, the George, help me here if you remember the log spirals, graphite log spiral, for example. I mean, there are several ways to use at the synchrotron to get large collection solid angle with high efficiency and 100-volt or 200-volt bandwidth, which might be enough to reject a lot of your elastic scatter. George, your thoughts?
Yeah, I mean, that sounds like a possibility as well. Yeah, that's kind of what I was asking. I mean, there's yeah, other ways to narrow the energy bandwidth, right, other than Herfty. So I didn't know if maybe there could be a happy medium between, you know, collecting really high resolution versus collecting everything, right? That might give you something overall optimally better.
Yeah, there may be a better middle ground.
Yeah.
Not losing too much, but gaining a little bit more. Yeah.
Okay, thanks, George. Matthew, you have a question?
Yeah, on the on one of these, you know, at least on the soft X-ray for the manganese, I noticed that some gratings often have an anti-resonance, where depending on the groove depth and so forth, such that the diffraction efficiency takes a big dip. Like for instance, on my beamline, the 5322, there's such a dip right at the manganese L edge. And so I wonder if it'd be possible to design the reflection zone plate with that feature, to cut out the oxygen and leave the manganese.
I see. I need to learn more from you about that. Yeah, any new ideas are highly appreciated for that experiment.
Yeah, so you would need to use some sort of software to calculate the parameters, and I don't know if it would actually work on a zone plate where the grading spacing varies across. It may only work on a plane grading.
Yeah, this is a first one was plane, and the other one's next one's curved. So,
well, I mean, it may only work on a grading with constant line spacing, as opposed to a zone plate. I don't know. I don't have the way of calculating that.
Yeah, maybe I'll catch you. I know where to find you. So,
yeah.
Okay, thank you, Matthew. Cheng Jun, you have a question?
Oh yeah, thanks. Very nice talk. If I recall correctly, the one graph you showed the X-ray emission for magnesium add, the incident energy is 9.5 keV. I wonder, is it limited by the source or any other reason you use such a high energy for the magnesium X-ray emission?
yeah, so we sometimes use 9 or 9.5 around that area energy range. The reason is that the immediate reason for us is that we want to do crystallography together, and beamline is kind of optimized for giving maximum energy, number of photons around that area.
Right.
That's one simple reason. There are other various reasons that we need to avoid a certain energy for Bragg peak, Bragg reflection that comes from the analyzer crystals, or avoiding Compton scattering. So many reasons together we are settled around that energy.
All right, thank you.
Okay.
All right, I'll ask the last question. I'll be very broad. So Photosystem II has had 20 years of work, and terrific progress has been made on it. The work you've done has shown how to push to very low concentrations. More XFELs are being built, repetition rates are going up. There's ability to do many more experiments. So if you were to guess, let's say 5 years in the future, what will be the exciting things to study in photochemistry that are only being enabled by the new improvements in the technology?
Right. Yeah. So as I mentioned, I think this Photosystem II is a good model system to study various things or develop multiple methods. So what we are learning is that, of course, there are more questions to be solved, becomes more fundamental questions we can ask for Photosystem II, which is a very interesting point we have. But what we are learning is that how this metal cluster and surroundings interact each other. So that's not only for metalloenzymes, but also important for other systems, inorganic systems as well. So how can we study the effect of environment for main photocatalytic reactions or other catalytic reactions? I think that those are challenges, and particularly for heterogeneous systems, there are much more difficulties. Molecular systems, it's relatively easy to study. So how to go into this photodynamics or structural studies of heterogeneous systems may be a challenge and interesting thing to do.
All right. With that, we all thank you for your time and for your seminar. That was it was great. I really appreciate it. I'll stop the recording now.